Welcome to the session. Greeting of the day. In today's class, we are going to talk about this infrared thermography and its various types. We already seen that there are topmost 8 NDT techniques which are in use in the industries, such as visual, liquid filtrant, magnetic particle testing, stereography, acoustic emissions, ultrasonic testing. In continuous with that, infrared thermography is also one of the important, that is our today's study. We have already seen the various types of thermographic inspections. On that, we are in the previous classes we have seen about this lock-in and pulsar modes. In today's class, in infrared thermography, in active method, in internal excitations method, we are going to talk about today the vibrothermography. It is nothing but we are using a technique of ultrasonic vibration generation. In that we have two modes such as burst modes and lock-in mode. This the top one, active internal excitations, vibrothermography, burst modes and lock-in modes we are going to see in today's lecture. Internal excitation methods. The energy is injected into the specimen in order to stimulate exclusively the defects. We are sending some infrared capturing devices, infrared camera. On the other end, the infrared camera captures the thermal variations, the heat distributions or concentration of heat at a point. But heat has to be generated first. For that, we are using some vibrations over the specimen. This vibrations makes the molecules to vibrate and to move here and there. This makes heat energy over the specimen. If there is a crack over there, it will be distributed and it will initiate the high point. So that we are going to capture through the camera. At all cases, the distribution of vibration will be uniform, and the point where the crack is available, there the change in the heat occurs. That change in heat concentration we are going to capture through the infrared camera. Camera is common. The methodology of initiating the energy is different here. We are using the vibration method using a ultrasonic machine setup. A vibrothermographic technique uses internal excitation to perform the inspection. You see one by one. In short, a vibration thermography, active methods, internal excitation. In short, generally we are calling it as a VT, a vibration thermography. It's okay. It's also known as ultrasound thermography. You see, the name came here, the ultrasound thermography, because we are using an ultrasonic source setup, a vibration setup, to create vibration over the specimen. It will be uniform over there and distributed over the specimen. Where the crack, it jumps. Where the crack, it reduces the heat or increases something, it will happen. Change in heat will happen there. That we need to identify it through the camera. Or otherwise, it is called as a thermosonics. The ultrasound wave is produced within the specimen by a transducer made up of a stack of a piezoelectric element. So the vibration, it's other type of techniques. How to generate this vibration? The clapping and all the material movements attacking makes the vibration. That is okay. Shaking causes the vibration. But how to create that? So for that we are using a transducer which contains inbuilt piezoelectric element. So that generates the vibrations. That's a separate study. Piezoelectric. The piezoelectric elements are concentrated in a titanium horn that acts like a hammer to hit. When we are keeping that hammer or horn over the specimen, it will keep on, it will vibrate. So that causes the action over the specimen also. After the elastic waves are injected to the specimen, the vibration is what will able to travel through the material until the defect is encounters, and the change of heat will occur. Therefore, travel through this material and dissipate their energy. So dissipating is the overall all energy through this period, mostly at the defect, because it have a jump there, it have a crack, it have a void crack. So the heat is locally released. That's what it is. It's also given here. It is locally released there. That is going to be the high point, releasing point. It searches some other contrast zones, the lower temperature, high temperature zones, to distribute that heat, to share it. So that is the point of where we have a crack. So that is the crack. And there's a void, there's an air gap. So that definitely it will jump from higher to lower temperatures. So those points will be distributed of a high energy point, so that we are going to capture to the camera. Any changes, lower changes or higher changes. So see, in this picture, we have a specimen and we have a vibration source here. Through that piezoelectric element is inside, and we generate vibration, and we are touching the specimen completely. 100% we have to touch. If there is any crack, then the calibrated point will change. If the calibrated points are changing, you see, we don't know what is 100, how much we are supplying. If more than 100, less than 100, or 80% is supplied, there is an error. You have to send 100%. Then what is the defect? Then there is a defect in specimen. If not calibrated point value is not say released, then how to find the crack 100%? So we have to perfectly touch the specimen. 100% vibration what is generated to be transferred to the job. So then vibration is connected again to the control unit. Simultaneously, how much vibration, 100% vibration is sent, and also accordingly this infrared camera also connected here to the PC, if it's computer, through which the image is generated. Yeah, just again the setup I would like to show you. Here we have ultrasonic signal generators, and it is touched over the specimens, and here the coupling where both specimen and the ultrasonic machine setup is touching 100% contact. So there we have a coupling. So coupling to be pakka to make 100% contact. So then we have over there, here we have a camera, because here the distribution takes place. Here the heat distribution takes place, and there's a crack insetting point. It generates more heat that is absorbed by the camera, and it is connected to the computer for processing the images. See, some few types are there. Maybe a stationary method, or maybe a mobile method. So here in this picture we have a stationary setup. Here this left side image we have a stationary setup where all the table dies are there, where we have to keep the sample and we have to check. Otherwise the other method, the right side one, mobile testing, mobile movement, we can take the sample in hand like a mobile phone or camera, we can take in hand. So few examples here I have given for our understanding. It means types of defects, whether it is detected or not detected. So see the porosity, first one, number 1 and 2. Number 1 and 2. Here the porosity is the point here where the number of points I am marking down here in red color. Number 1, porosity and toe cracks. The toe cracks are here. At this point the toe cracks here and here. The toe cracks here. The line. This is the corner of the weld joint. It's called as toe crack. Here the porosity is not detected and the crack point is detected because it is having a crack longer version. The heat can be easily distribute over there, release over the air point, high insertion point. That way the color itself will vary. In the simulated one, when we are seeing through the camera, it gives multiple colors. In the first previous slide we have seen one aircraft flight which have more stress at the front and minimum temperature at the back side. Similarly here, when there is a higher crack, longer crack, it generates more heat, more high temperature colors will be visible. So easy to detect. Similarly, see here the crack, the root crack At bottom it is available. Here this one root crack, it is a well joint, V groove at the bottom, the root is at the bottom, so the face is at the top. We know all these things. So this root crack at the bottom we can able to detect because it is a longer one. Lack of root fusion, it is detected, longer one. Root fusion is not even welded. 100% of total thickness 30, maybe 28 mm is already welded. Remaining 2 mm is not welded. So the laminations not detected, and the toe crack again here, the crack is there. So it is probably detected. So these are some of the examples of vibrothermography, how it is useful in the industry. That is nothing but a welding. See, the thermal waves will travel by the conduction to the surface where they can be detected with the infrared camera. So initially we are remembering this what we have studied in the previous slides. We are supplying in contact 100% contact the in ultrasonic vibrations. When the vibration is then traveled through the conduction method to all over the specimen, and it has been whether the crack is present or not present, all are detected by the infrared camera techniques. It's very simple. You see, we are giving vibrations, so these vibrations are accumulating at a defect because it's a free point. It's a air releasing point, free point. It is accumulating at the defect point. Other point is traveling at surface, smooth surface. It is traveling one on one. It's traveling, but at the vacant point, it is not possible to move. Vibration is jumping. Not possible to transfer its energy from one end to the another because its cavity is there. So at that point, it is accumulating. All the molecules are coming there and it's accumulating. Vibration is nothing but a movement of molecules, energizing the molecule to move, to push. But where it will be pushed? It is want to push from one end to another end until the other end to be free. If there is a crack, where it will move, that the specimen is ending point. Therefore, it accumulated there where the crack is there. So that is a accumulating point of more molecules, more energy, more heat. It would automatically show on the infrared camera able to find. So different points getting heated up. So therefore heated up. Later what we are doing, the infrared camera which does the thermal imaging and exactly locating where the defect is actually present, because heat distribution is understood on the simulated image, but where the concentration, the temperature difference, color image will be easily taken from the picture. So there are few configurations configurations of the thermography. There are two methods are there in this vibration thermography, vibrothermograph. There are number one is a burst mode, and number two is the analog mode. So analog to pulse thermography, analog to the lock-in thermography. This pulse mode and lock-in thermography we have already seen. There we need some a few understanding here. In vibrothermography, the source of energy is different. The source of energy is here the vibration, ultrasonic. But another two methods we have seen. One is photographic flash lamp method. One is the periodic lighting of a halogen lamp method. So now we can understand there are three methods of heat source are there: halogen method, flash lamp method, and this vibration method. But at the end output we are taking only common method of infrared camera. So heat detection method, but heat generation method is different. So on that here we have understood that in the vibration method we have a burst mode. Burst mode is nothing but analog to pulse thermography. Here the lock-in method, immediately lock-in, it's a halogen lamp we are using a periodical way. So there are two combination of possibilities are there. So vibrothermography capturing method. Generating method is 3. Capturing method is infrared. So that is why it is named burst method. Maybe a heat source generation is ultrasonic, but capturing method is infrared. We understand like that. So see, we have two methods here of in this picture. In this picture you see number 1 as vibrothermography, number 2 as Lockin thermography. Here the input signals are generally straight, there is no difference. The amplitude, the frequency, what they're supplied, the energy generated are uniform, and it is uniformly falling on the specimen. That is generated by the ultrasonic transducer. The vibration is generated is uniform. 100% of amplitude is given to the specimen, 100% of frequency is generated, keep on it is coming. There is no change. So with respect to this change, we are recording the responses, how the defects are there. Whenever the defect is there, it increases. So the response signals will be in such a way like this. Infrared camera is capturing here. Burst mode. So burst mode we are using some pulsed thermography. It is given in the PPT also. It is pulsed thermograph we are using. Next one, Lockin mode. See in the right side image it belongs to a Lockin mode. The right side Lockin mode. Here we are changing the amplitude and frequency and verifying. What happens when we are trying to give the uniform one? Some defects may or may not detected, because sometimes we need a change in amplitude to identify two defects, maybe a minimum micro defects or maybe a large defects. The uniform amplitude and frequency supplied may be enough to identify a larger crack, but may not be enough to identify a smaller micro cracks. Therefore, this lock-in method, it means a lock-in word we are using to concentration mode, a specific point mode. In the previous class itself we have used that word. So lock-in a specific mode, we want to find a specific defect here. Then what we are doing, we are trying to change the amplitude, we are trying to change the frequency up and down, larger and smaller both we are supplying. Maybe a large defect may be detected, not detected. Smaller defect may be detected, may be not detected. But combinedly, we have to supply two terminologies of large and smaller to identify irrespective of small or large. Any one defect we can able to identify there. So when it is amplitude is large defect or smaller normal defect can be detected, identified. When it is a change of amplitude happens or to small or to be enlarged one, the micro cracks will be possible to detect. As it is high amplitude, it can able to concentrate more at a specific point. So high heat it is initiated, we are supplying more energy there, even the micro cracks also will be identified. So that is how it is Lockin vibrothermography. So that is what the thing. Input signals is given by ultrasonic transducers, and the maximum peaks for the same means we are not going to change the amplitude and we are not going to change the frequency. It is uniform. It is uniform. So that is what we got some understanding. And next one is the Lockin thermography. You see, the Lockin thermography. In this case, we are changing the amplitude, changing the amplitude, and changing the frequency. Here, going to get two different graphs. Two different graphs at a high amplitude one graph, or otherwise a uniform amplitude one graph, and we are changing the amplitude low level or maybe or high level, we are getting multiple graphs. So at any one graph we will get some defects. Therefore there are multiple chances are there to identify at the same point when the high amplitude is supplied one graph, maybe at the time one defect. When we are supplying the low amplitude or very large amplitudes, and one more graph is plotted over there according to those response signals. So again it is chance of identifying the defect at the same point. So there are we are creating multiple chances on the Lockin vibrothermography. So that is what the Lockin method is better than that of the pulsed mode. So here going to get two different graphs by which we are going to get the exact location. A Lockin vibrothermography is giving a more accurate results. What written here also accurate results than that of the burst mode. So that is something pulse we have used. So in the graph also you can see multiple graphs we are getting. The red color dotted lines one, the graph here, dotted and other curve. The advantages in either burst mode or the lock-in modes, extreme it's all both are fast technique because of flash or maybe the bursting or maybe the ultrasonic vibrations. All methods are at tremendous fast technique. That's one of the very good advantage. Defect detection is independent from its orientations inside the specimen, and both internal and often the surface defects can be detected. So both we are doing internal defects or maybe the subsurface defects. Usually we have used the subsurface radiography we have used. So but here we are classified like that only in the previous classes and the beginning of the class also. Surface defects, liquid filtrant, and then anti-particle dusting, subsurface defects, the radiography like that. But here this thermography method, vibrothermography especially, can able to find internal defects also and subsurface near surface also, or otherwise the surface also can be detected. It is the most appropriate technique to inspect some of the types like called a micro cracks, a delamination. You see, micro crack came here. We talked vibrothermography, we are getting multiple graphs, therefore micro cracks also possible, we told. So the same point here. There is only a minimal heating of the inspected specimen since the energy is usually dissipated mostly at the defective areas. Means we are using accurate and precise methods, or we can able to get therefore. See, every method has its own disadvantages. It is necessary to relocate the transducer to cover large area. If it is large area, definitely the vibration will get reduction. It's normal. Therefore, it's 100% calibrated. 100% vibration can be useful for certain volume of area. So for every zone, we have to change the spot and we have to generate the vibrations here and there. For inspections, hence vibrothermography is only suitable for relatively small objects. Need of a coupling media between the sample and transducers. Yes, because it's 100% contact to be there. If it is not 100%, definitely the calibrated vibrations will not transfer to the specimen. Then there will be the error. Need a holding of the specimen itself. Specimen should be held first, but it is common for all. A bad coupling implies a poor ultrasonic transmission, vibration transmission, but more precisely, it creates some unwanted heat also. Not only it is suppressing the ultrasonic vibration to the specimen, but also it generates the unwanted, because that itself assumed as crack. We should be in 100% contact. We are not in contact. That itself is understand it's a small crack or any other gap. It means air jumps. Therefore, it also generates a heat insertion point there itself. At the vicinity of the ultrasonic inspection point, your ultrasonic horn should be clearly touched your sample. There should not any gap problems. Yes, that is what we 100% touching to be there. So you can able to see a few some application images regarding a general thermography, maybe a pulse mode, maybe this burst mode, or maybe this all any thermography types, maybe any lamps are used. So generally the applications, you see here we are using some pipes manufacturing. We are understanding where the heat is achieved, heated the casting or non-heated conditions. Here in this image, some of the panels or electronic gadgets are verified at this temperature level. Here you can see in the Fahrenheit, the lower darker zones are in the 85.4 Fahrenheit. At the same time, the brighter zones at the top, see, at the top, brighter zones, it is temperature around 125 Fahrenheit. It is 85 Fahrenheit to 125 direct increase. It means a brighter color. We understood that it belongs to high temperature. You see, at the right side, this image, we have a refrigeration condition system. a general setup of a refrigeration condition system, and how far it is heated to generate a cooling systems or any heating systems, how it is working principles. It may be we can able to take for our engine car engines also a similar type. We have taken some pictures showing here taken from YouTube's and other company where the images are the camera production company. These images are taken from the camera production company. So that at center point here, so this zone is very brighter, showing it is a representation at a high temperature. So here, this is the last image. You can see there a specimen is checking over there. So they have kept some specimens inside, and they are concentrating to take data readings. Some of the examples I have included here for some of your references. See some wheel alignment setup. The wheel tire has been high temperature because it is traveling and rolling over the friction is happening between the roads and the rolling tires. And simultaneously the alloy wheels also heated. So those things are shown in this picture. Just we are using thermography, we are taking camera and analyzing how much. Definitely it is showing the brighter color. See, the lower color is 46 degrees centigrade. At the same time, the brighter color is 60 degrees centigrade. So it is showing simultaneously. Similarly, the other images of cars or maybe the field works or maybe any rolling operations or any compression operations. See, it is a FLIR is a company of topmost international brand creating of this infrared cameras. From there only we have taken that picture, and also this operations of the machine setups, the military using vehicles. Likewise, we can able to understand those applications. Here further, I would like to add one small YouTube clip. Credits goes to the YouTuber, and I am adding a YouTube clip for our understanding of this video lecture. It's a 3 minutes video. It will refresh you. So see, these are some of the examples that I would like to share with you regarding this any methods. It may be a flash method or burst method, vibrothermography. A general applications I have shown you in this small video clip. In this class, we have seen about active methods, internal excitations, vibrothermography, and those sub-classifications. Right? Remaining part of the subjects, we'll see you in the next session. Thank you.